Phew. That's a full screen. Great. Okay. Well, just thanks to everybody for showing up. It's we're down to the core constituencies, I said. But anyway, hopefully this will also be useful more broadly. So this lecture is really going to be about, oops, it's not wanting to respond to me. There we go. It's really about looking at the sort of geometric structure of a superstratum that you see throughout the literature. I just pulled this out of one of my more recent papers. But doing it by going through an example and talking about all the different steps, but all the different features. So I'm really going to look at what underlies this picture and pictures like this thing. So let me just remind you where we were. So we were looking for the six-dimensional geometry. Well, 2B, we're throwing away the T4. We're looking at six-dimensional geometry. We're taking this base metric here to be flat in these funny coordinates. We have this function sigma, which was ubiquitous, and it basically describes the edge of the disk where we're going to have some supertube sitting. We put along the supertube locus at sigma equals 0. There's the source of this Kaluza-Klein monopole. And we put some angular momentum on it, tuned in exactly such a way that you satisfy these relations, regularity relations, and the whole thing turns into global AdS3 times S3. But you should think of this as a sort of substrate on which we're going to put momentum waves to this particular supertube ground state. That was sort of key points of last lecture or so. Now, these momentum modes are encoded in electrostatic potentials and magnetic two forms on this base. And I gave you the building blocks last time. There are several classes of these sort of classic solutions built out of mode by mode pieces. The modes are, as this is the coordinate on the sort of AdS3 direction, this is on the two sphere, and then there are these mode functions that decorate everything. And we have these two classes of these solutions to these flux equations that dictate the fluxes. And then in the standard superstratum, what we do is we have the original background D1, D5 charges of the supertube, but now we decorate things with the fluxes. And in particular, what we do, because we know what the holographic dual is, but you could do something more general, is that we don't touch Z2 and theta1, but we then touch, or we add fluctuating modes in the most general form to Z4 and theta4, Z4 there, theta4 here, and also to Z1 and theta2. We throw those in. But then you start solving the BPS equations, and you immediately find the constraint that tells you some of these constraint functions, but then you have to solve the second layer. I talked about how to do that last time. Basically, we know all of these sources, and we basically have to determine the metric components, omega and f from this. And the sources here are these functions, as I've written down, but we impose these Quaffurian constraints. It's required, these seems to be required by regularity, but what it means in practice is that you get to freely choose Z4 and theta4, and then it determines Z1 and theta2, which are the prime quantities in this thing, entirely in terms of the quantities that turn up here. And as I said last time, this gives you in principle, two arbitrary functions of three variables. So basically, what this does, as I said last time, is that you get rid of all the situations where the modes sum and you only get the difference modes. But at the end of the day, you get with this procedure, you should get two arbitrary functions of three variables in Z4, theta4, and then away you go. And the way to think about this is that this is really, in some sense, an NSB field. It's the stringy mode and it's the seed, and then this is the D-brane response that's constrained at quadratic order because this is quadratic constraint. Okay, so what I'm going to do is illustrate this with what's called the 10N superstratum. And this has become the workhorse of this subject because it's one of the easiest ones to construct. It's one of the easiest ones to understand. And it's got some remarkable properties. So I'm going to go through, we'll talk about the solution and then go through and talk about a lot of its properties. Okay, so the moding is basically given by VKMN. And the first thing to notice is the only quantum number that's going to be arbitrary is n, and it multiplies v. And so that descends into essentially this function, complex variable psi. The phi1 and phi2, roughly speaking, descend into the other complex variables, and we're going to have k as 1. we're going to have k as 1, and that's going to give us a single factor of chi in front of our thing, but the general power of n is going to mean that we're going to have a solution which is a generic Fourier series in xi. So the 1, 0, n superstratum family, if you like, is the set of all things that are basically made out of this single holomorphic function, which basically means that Z4 and theta4 are going to have that plugged into it. And there are going to be two functions messing around, flying around, one of which is the fundamental function f, and then there's another function g, which is simply chi times that, and it's just decorated by this factor of sine theta. That's to do with the actual supertube, underlying supertube state that you're exciting. So k equals 1, m equals 0 defines a supertube state, and then this defines a bunch of excitations on it. Okay, so the seed is very, very simple. If you write it in this complex form, basically Z4 becomes the real part of this holomorphic function, and there's just a single sourcing term. And theta's a tad more complicated. It's basically the derivative. Remember, I said if you write these in holomorphic function forms, basically the fluxes are usually derivatives or primitives you may have to integrate up in terms of this underlying function g. And then there's a little bit of more complicated decoration buried inside the form of this omega 1. And remember, these omegas are a standard basis of two self-dual 2 forms on R4. But the takeaway message is writing this, as you'll see, in complex form makes things a lot more simple, particularly for this solution. Now, coiffuring. Remember, I sort of said that there's a quadratic, the Z1 theta 2 are quadratically constrained in terms of Z1 theta 1. And in holomorphic language, it's incredibly simple. It's just the same expression where you replace the holomorphic function g by g squared, which says that basically this mode turns up in Z1 theta 2 as the square of this function. It's not always that simple, but it's pretty close. So in this 1, 0, n, I said it was going to be simple. It really is pretty simple. The coiffuring constraints tell you take Z4 theta 4 and replace g by g squared, and you are done. Okay, now the unmodified part, of course, is the bit we're not going to excite. And then there's the constraint. And then if you look at the constraint, you see that this is, remember, this is Z1, Z2 minus Z4 squared. Well, you see what happens if you take Z4 squared, you get g squared, g bar squared, and g bar. And all this does is it means the only bit that survives is g bar. So the metric, as I said, likes to be sort of 1-1 structure rather than a 2-0 structure. It likes modulus squareds or derivatives with respect to one holomorphic leg or another. So in the first case, the constraint is very, very simple. Okay, now the differential equations. I'm going to show you what these things look like. So the first thing you do is you solve it in terms of this basis that I've talked about, which is the omegas. So and then you start decomposing everything mode by mode. And it turns out that this is the nice way to do it. You write the oscillating modes in terms of sine and theta components and make them sine, make them cosine. You could do it the other way around. You can make this cosine and sine, and then this will become sine. You just have to see how, when you differentiate things, the V derivatives land here and see how the sines and cosines distribute themselves. So you just expand in modes and do it mode by mode. And then you do the same with the differential operators. You take this left-hand side, we're going to look at only the oscillating parts of everybody, and then you decompose this operator, because it's a 2 form, into, and it's a self-dual 2 form, and this is a self-dual 2 form. It must be decomposable into this basis of self-dual 2 forms. And you define these operators, which I'm going to write down in a minute, L1, L2, and L3. And similarly, this is a second-order differential operator on F, or a divergence on omega. And so we're going to decompose this operator in exactly the same way. It's a scalar operator, and it's going to be some complicated thing called L4, which is going to be a mixture of a Laplacian and a divergence, which we'll see in a minute. And you do exactly the same thing for the sources, and then you get this differential operator equal to the omega 1 part of this source, and so forth. So you just do the obvious component by component self-dual part of this, and similarly you write down this fairly complicated source on this part of the equation. So the operators, here they are in gory detail. So but the point is they're first order differential operators, and they're kind of obvious intuitive things. This is sort of like, this is d of omega. And basically everything here is all the possible pieces of d of omega and then star d of omega. And then there's all the moding. which turns up because we've assumed a particular mode. And this guy's a little bit more complicated because, as I said, there's a piece of this which is just the Laplacian and those funny coordinates on R4, and then this is the covariant divergence. You see, it's basically the same as this. You get this operator by replacing omega by derivatives of f, and so this is the divergence of omega, but it's the covariant divergence of omega.
Nick?
So yeah.
When you say differential operators, these have already acted on something.
Yes, so let me just back it up. I'm taking this form for omega, and I'm shoving it in there.
Yeah, okay.
And so here are my component functions. There are the hats indicate the component pieces in this oscillatory form, and f hat is the component piece. So they're acting precisely on these pieces that I've written in auxiliary form, and I've just separated out all the mode dependence, which is m, n, and n. I haven't actually specified to 1, 0, n yet.
Yeah.
No, L1 is actually L1 acting on omega already.
Yeah, yeah, sorry, I should have, I think I just said this.
Differential operator, I imagine something that you have to act on something.
Yes, indeed. And in fact, I've actually hidden it in here. This is a differential operator acting on omega because I didn't put it acting on anything. I just said, whatever turns up here, I'm going to call L1.
So L1 is not an operator. L1 is just a name for it.
L1 is a name for an operator acting on omega and f. I should have said it differently. Sorry, indeed. But what I mean literally is L1 is the coefficient of this term in this expression. And L2 is the coefficient of this term the coefficient of omega 2 in this expression, and so forth. And it's differential operators acting on omega. F hat turns up here, F hat turns up here, and this is a bit of a pain. It's basically the covariant Laplacian and the divergence. So this is the system on the left-hand side of all the equations you have to solve. Come to the right-hand side in due course. But the thing I want to remind you of is something I said last time, and now it's absolutely manifest. Because you've gone to a mode basis, there are two equations, L2 and L3, in which omega r and omega theta only turn up algebraically. They're not differentiated. They're differentiated in this, and they're differentiated here, but here they turn up algebraically. So therefore, you just turn it around and invert. You use these two equations to write omega r and omega theta in terms of everybody else, and then you shove that result in here, and you shove it in here. And so basically, you get two second-order PDEs in omega 1 and omega 2, and I described last time how you set about solving that, but that's the sort of structural feature that I wanted to advertise here. So, and you're doing the same thing on the right-hand sides with the sources. So as you manipulate this, you of course manipulate the sources in the same way. Now, the last part of this, remember, is this is 4 equations for 5 unknowns, the 4 components of omega and the function f. But you've got to remember you've got a gauge choice. The most simplest version of this is if it's non-trivial v dependence, is we just get rid of f by integrating this back and saying, okay, if it's oscillating in v, you can find a primitive and away you go, you get rid of f. So 1, 0, n superstratum, what actually happens here? Everything gets really nice because it makes life very, very simple. When this quantum number is fixed and this is 0, then remember, coefficient gets rid of the sum modes. So therefore, all that survives are the difference modes. And that means these numbers k and m are both 0 in the difference modes. So only differences of n1 and n2 appear. Now, if n1 is not equal to n2, then you can choose f as 0. And here's the system you actually need to solve with the sources. That has no source. This is a source that turns up, and so forth. This is a source that turns up. So at the end of the day, this is the system you have to solve for the oscillatory modes. And if n1 equals n2, then you can sort of see it from here. I've dropped the f terms, but you see an awful lot of this falls away. An awful lot of this vanishes when n1 is equal to n2. And there are some things that survive. But if n1 is not equal to n2, this is a relatively tame differential equation to solve, as is this, and so forth. And the procedure just goes straight forward. And the sources are particularly, relatively simple. When n1 is equal to n2, let's just step back a second. When n1 is equal to n2, essentially the equation for f decouples. Let me just show you where it comes from. The equation, when n1 is equal to n2, that means there's no oscillatory mode. And therefore, this omega dot disappears out of this equation. This becomes the Laplacian on f is equal to some source. And all the v derivatives vanish too. So the source is here. So basically, when n1 is equal to n2, the system becomes even more tame. First of all, the equation for f decouples. So it becomes this very simple Laplacian. There's one little residual mode term. That's from k, taking k, it says, I think k is, well, there's some residual mode term. And then there's a really simple source. You can solve that. It's elementary for f, and then you substitute it back into the equations for omega. And the equations for omega are, again, rather simple. And particularly, if you look at this one, you see that this implies that that's the integrability condition for this, to say that omega r and omega theta are pure gauge. So at the end of the day, you take omega r is equal to omega theta 0, because they're pure gauge, and then you wind up with two really rather simple differential equations to solve. So in this particular instance, the differential equations are very simple. They collapse to something manageable, and you can solve it in a few hours, or even quicker if you use the holomorphic formulation. So I'm going to talk about the, what the solution is, and you'll see how startlingly simple it is. The underlying functions, remember, are this holomorphic function, which is all the modes of the n. And then there's its friend, which is just that multiplied by chi. And Z4, remember, basically is the real part of that function, g. And theta 4 is similar. The metric pieces we're looking for, P, omega, and F. And as I've said a million times, we also know, excuse me, what beta is. And as I said a million times, we know what P is because of the constraints. So we know exactly what it is in terms of G. The second layer solution is unbelievably beautifully simple. It's simply that. And when written in this, if you do it mode by mode, it's a bit more disgusting, but that's the way I set it up. But if you write it in the holomorphic form, it tells you that this function you've been looking for is simply the modulus squared of f plus a constant which you can get to choose. That's one of these homogeneous solutions. It's the simplest example of what you have to do with a homogeneous solution. And it's going to play a major role in due course. And then what happens is you have this piece from the supertube. This is a harmonic piece, which tells you the background was a supertube. And then these sources all generate the same combination times sine squared theta d phi 1. And so all that long and song and dance for the superstratum in the 1, 0, n solution, it's unbelievably simple at the end of the day, and it's beautifully holomorphic. It's the function f that turns up here is the modulus squared of the underlying oscillation functions. That's why I kept saying, yeah, go ahead.
No, I just had a question. How do you know that there's no d phi 2 and no d theta?
You solve the equations.
Is it obvious or?
No, it's not altogether obvious. You just get into the equations and you start solving. And maybe there's if you write it in holomorphic form, it's actually much easier to see what's going on because you start seeing this sort of thing. Basically, the second order differential equation that this thing satisfies involves a dd bar with respect to psi, and you sort of see how that emerges from the sources. So in the holomorphic form, it's more obvious, but it really is. You know, you have to go through the procedure I was outlining. You've got these differential equations to solve. And you start by doing the elimination I was describing, then reduce it to second order differential equations in omega. And then what happens is you then look for the equation for omega 1 plus omega 2. That turns into a plus equation. And it tells you that the function you've got at the end of the day really is sine squared theta times something or other. In fact, if you're smart, you'll put in the fact that the sine squared theta always multiplies the d phi 1. It's a regularity condition. And if you don't get sine squared theta multiplying d phi 1, you've got a singular solution and you've got a problem. So you always know that because of the pinch off from the d phi 1 circle, you've got to be sine squared theta. So you always pretty much, when you start solving it, throw that in as a given. And usually you throw in a cosine squared theta in front of d phi 2 as a given. So when you look at omega 1 plus omega 2, the sine squared becomes sine squared plus cosine squared theta, and you get a differential equation for omega 1 plus omega 2, and you discover it's exactly the same as f. So it really is, once you do this heavy lifting procedure at the end of the day, for this particular class of superstrata, it collapses almost to a triviality. I remember thinking, do I really want to do this one day, and started doing it, and 2 hours later, I had the complete solution.
So actually, it almost looks like a single two-charge supertube, but with more rotation in one. I mean, essentially, it's rotating more than the BPS value. So a single, the original two-charge supertube is just omega 0, and the supertube stays in the plane in either the phi 1 or the phi 2 plane. I forgot in which one.
It's in the,
but it looks like it's as if you are basically underspinning the supertube a bit.
That's an interesting point. I mean, the supertube is in the phi 1 plane, because remember the supertube is r is 0, theta is equal to pi on 2. So this guy goes away, and it's really here, d phi 1. And so d phi 1 is the supertube direction, theta is pi on 2 is where it's located.
So it almost looks like you're putting more momentum on the, more angular momentum on the supertube, actually.
It does look like that, except it's a momentum wave because it's also here.
No, it's also momentum. So somehow you have both momentum in the y and the angular momentum, and and that should come together.
We're gonna no, it doesn't work that way. We're gonna come to that in a minute. And here's the
actually they go against each other. You can actually see that they go against each other.
Oh, hold a sec. There's something else to notice here. There's we haven't chosen this C, and we have to. We're going to compute. I'm going to show you how to calculate the angular momentum charge on this right next. So just bear with me, and we'll come back to this question. But the point is, this does not contribute to the angular momentum when we're done. You're going to see how that happens. It looks like it does, but it doesn't. Sorry, other question? Yeah.
Is there a build notation going on? We made a gauge choice which sets curly f to 0.
Yes. We're going to undo that. We're going to undo that. That was for the purpose of solving. Now we have to go back and ask about what happens to regularity, and have we chosen in that gauge choice? Remember, the gauge choice has to do with redefining the u coordinate.
Yes.
And if we made a stupid definition of the u coordinate, infinity is going to look like crap, and that's what we're about to find, and we have to fix that.
Yes. So my confusion is we've set curly f to 0, but then we are solving for it. How does that work?
No, hold a sec. Remember, there are two parts of the statement, and this is also important. The difference modes. If n1 and n2 is not equal to 0, you can choose f to be 0. Okay? And you have to solve this, and this gives you a whole pile of stuff. If n1 and n2 is 0, you also have to solve for f. F does not go to 0. You can't choose a gauge to make it 0. Because remember what the gauge choice is. If things that don't depend on v can't be removed by gauge choices. So there's always a piece of f that doesn't depend on v, and then there's a piece that does. So we've chosen it, and so we have made some gauge choices here, and I've tidied. In fact, I've tidied it up a little bit. But basically, when you first do this, you go, oh, there's a nice gauge choice, f is 0, and then you realize it's a weird looking solution. Then you fix the gauge choice back. So in some choice of gauge, this is the right solution. However, it's the cleanest way to write the solution. And now we're going to undo some gauge choices. You're going to see what I'm about to do, but this is the cleanest way to write the solution. And you see what looked like a terrifying thing in terms of all these oscillations. The metric collapses to something that's, as Joseph was just remarking, it's like a minimally decorated supertube. All that's happened is that the f function has now got some non-constant pieces, and it's got some, and the warp factor's got some deformation, but it's just like a deformed supertube. So I'm now going to spend the next bit of talk talking about regularity, and we've got a whole bunch of things to do. I'm only going to do a few of them, but we want asymptotically ADS 3 times S3, and that means the function f's got to go to 0 to infinity. And that means we should look at what this is doing as infinity, and in particular, if we define f infinity of v as being the limit of r goes to infinity of f xi, but remember that's the same as modulus of xi goes to 1, and that is simply this Fourier series. So as you go to infinity, you have this momentum wave with this Fourier series. The bn's have to fall off as n gets larger. Oops, there's an n missing in that exponent, I'm sorry. It should be e to the in. So basically, you wind up with that Fourier series, and this is going to be the thing we're going to focus on because it's the modulus squared of this quantity that survives infinity. We got to get rid of it. So the first thing we do is we remove the root mean square part of this. In other words, I literally take the integral of this normalized around the circle dv. I want to remove the constant piece of this. So that's how you pick c. So that f will actually have no constant piece. So the only piece of f that's left at infinity is the oscillating piece. And then what you do is you remove the rest by a gauge transformation. You remove the constant piece out of f. So now you can integrate this up and basically take the indefinite integral of this thing so that ddv of this is given by the oscillating piece, and it cancels in this thing. So at the end of the day, if you want the correct result that has nice asymptotics at infinity, in other words, F dies at infinity, and also similarly omega dies at infinity, then you have to basically pick the, you have to do this trick. So first things first, note the function C has been fixed by removing the RMS pieces of F at infinity. That's very important. There's some real physics buried in that. And then the second thing we've done is that another way of saying what it is remember, the gauge transformation comes from redefining U. And you can always redefine U so that it isn't, you know, at infinity you want du dv. But if you've got some other garbage at infinity, which is where it's du dv plus something times dv, it's not flat, then you've chosen the wrong U coordinate. And what I'm saying here is, if you want the good asymptotics at infinity, you want 2 du dv and nothing else at infinity, then you've got to make this 0. And to make this 0, you have to remove all this oscillatory crap and the constant stuff. And so that fixes the constant C, and it also fixes the gauge, if you want a nice gauge at infinity. Now, I'm not going to talk about this here, but there are sometimes some reasons when you go to the middle, the U coordinate needs to be redefined again to look at some other regularity conditions in the center and so forth. And it's sometimes convenient to change the gauge back when you go to other regions of the space. But if you want something good at infinity, here is the final solution. It's F so that it falls off at infinity, omega so that it falls off at infinity, and so forth. Bogdan, I think I've answered your question now, haven't I?
Yes, Nick, you have, but I have another one if you want me.
Oh, go for it, yeah.
You referred to this C earlier, and in your paper you referred to it as a homogeneous solution. So
yep.
If I take this C that you've given here and I plug it in the homogeneous equation,
it's 0, it dies.
Okay.
And it's simply because F is always differentiated. So this is a really trivial homogeneous solution.
Yeah, I mean, yeah, sure. Yeah, I mean, it's just, yeah, okay, of course.
So that's regularity part 1. So regularity means make sure it has the right asymptotics at infinity. Regularity 2 is we want to make sure it behaves properly in the middle of the space. And so the number one place you want to look is the supertube locus, because that's where all the sources are. And you want the thing to be smooth at the supertube locus. And that means R is 0, theta is equal to pi on 2. Now, the dangerous part is precisely this part that goes around the edge of the disk. And so all I'm going to do is I'm going to isolate that. The rest of it goes along for a ride, but this is the dangerous part. So let's look at what that is. The dangerous part is simply, essentially, this is the d phi part of beta. This is the d phi 1 part of omega 1. And this is again the d phi part of beta multiplied by the half f. And then there's also a piece where you have r squared a squared sine squared theta d phi 1 squared times root p. So these are all the coefficients of d phi 1 squared terms in that metric. And the thing to notice is there are a bunch of singular functions there. When sigma goes to 0, this goes to 0, this goes to 0, and this has some 1 over sigmas in it. So you've got to worry about that too. So you shove in the solution along with the constrained piece like this. And then this whole thing becomes a rather complicated beast. This is basically the root p, or this is 1 over root p, so I've pulled this out. And then there's some stuff which is just a collection of all the rest of it. There's a piece which is p, which gives rise to this, and then all this stuff here gives rise to this. Mercifully, the f infinities and all that kind of stuff, and the f's cancel out between essentially the f here and the omega 1. So basically all you're left with is this. And the thing to notice is there is still potentially a singularity. So this is in general what you would get. You would have a singular source along the supertube. But remember, this locus is r is 0, theta is pi on 2. So r is 0 gives you q1, q5, a squared here. Theta is pi on 2, that turns it to 1. So you have to relate this to this. And so you can remove the singularity by the simple expedient of setting this quantity equal to this quantity when r is 0 and theta is pi on 2. And then it will cancel that. In fact, if you do that, this term turns into nothing other than q1, q5 times sigma, which exactly cancels this sigma. And the end result is the coefficient of d phi 1 squared becomes a completely regular object, which is just this root p times, then there's a sigma squared to the half, whoops. Oh yeah, sorry, root p has a 1 over sigma, so a 1 over sigma squared. So this factor is just another way of writing this. So this is the supertube regularity condition, but also notice that it, in fact, this is the condition. Oops, this is supertube regularity. Previously, for a supertube, we had Q1, Q5 over Ry squared was A squared, but now we have to set it to this quantity A squared plus a half C. This RMS part of the function f contributes directly to this regularity condition. Okay, now, basically, there's a third part to the regularity story. We have the superstratum regularity at this point. What we're going to do is just unpack this a little bit further, because one of the other things we need to do is to make sure that this isn't doing anything bad inside the solution. In principle, this is a difference, and this could go negative if f is big enough. And what I'm going to do is show that this is always positive definite inside the metric. So these crazy factors of root p that turn up everywhere, and you never get a root of a negative number. So the last part of the regularity is to show that this is always positive. And it follows from the same superstratum regularity condition. And it's rather easy to do in this case. Sometimes you have to work fairly hard at this. So what I want to do is unpack this. So this is the regularity condition we just got. But remember, C, because of regularity infinity, is constrained to be this RMS value of the function f at infinity. But when you actually expand that in modes, you can go back to the original Fourier series, you see that it is nothing other than the sort of L2 norm, if you like, of this beast. It's a half sum over all the Fourier coefficients squared. So that's the regularity condition. Now, positivity of the warp factor. I'm going to write this thing in terms of these magic coordinates xi. And I want to look at the Cauchy-Schwarz inequality applied to modulus of f squared. I want to unpack this thing in terms of this beast. Now, the Cauchy-Schwarz inequality says the sum of a plus b modulus squared is always less than the a squared plus b squared, and applied to a much longer vector, it's the dot product of the vector b with the vector, so psi, if you like, basically is always bounded by this. Now you pull out this factor, and you realize this is just a geometric series for the inverse of this. So this and this cancel, and then you wind up with the sum of b squared. But this regularity condition tells you that the half sum of the b squareds is less than this by an amount a squared. So this is always uniformly bounded below. And so the solution is completely free of singularities. There's no danger. This term never, ever, ever goes negative. Sometimes you have to work hard to get this. And then there's the question of absence of closed time-like curves once you've done this. And that takes a bit more effort because for simple f's, it's easy. But for a generic f, we had to work quite hard to prove this. And I'm not going to discuss it here. It's in the paper that we wrote on this subject. So supertube regularity. The last part of this is to look at the charges. And remember what you're supposed to do. You're supposed to look at the sort of leading terms in F. You ignore oscillating terms because they'll average to 0 over any compact circle. And then you look at subleading pieces. And then for the angular momentum, you read them off from, it turns out to be beta plus omega. And you ignore all oscillating terms. So we put in this and look at what we get. So by construction infinity, we've killed off all the oscillating terms here. And then QP is simply given by taking the appropriate integral of this quantity, pulling out the appropriate coefficients of this, and you find that it is nothing other than the sum of the bn squared weighted by n. That's just because you're doing a second order Taylor expansion of this function f at infinity. And so, first, it's the first term in the Taylor expansion of this quantity. So you get derivative of f times f, and that's what this is all about. So straightforwardly, the momentum charge, and notice the appearance of n. So the sum of b squareds. So it's important to, these n's are actually important to you. The Q1, Q5 condition, the supertube regularity condition, constrains the charges to the sums of bn squareds without the factor of n. So the independence of the momentum charge from the supertube regularity constraint has everything to do with the fact that there's an n here. So those n's actually tell you how the QP differs from Q1, Q5. Okay, so that was easy. And then it turns out that the J left and J right are exactly what they were for the supertube. And it's fairly easy to see how that happens. Basically, what you do is you look at this term and you realize since you removed all the stuff at infinity, this is 1 over r. And then this thing, therefore, and this is already 1 over r squared. So this is a 1 over r cubed term. So this is in the subleading class. Actually, this is 1 over r squared, I'm sorry. So therefore, it's 1 over r to the 4th. It's in here. So that's subleading. There's still this stuff, but basically you look at this and you realize this is purely oscillating. You remove the RMS stuff. And all you've got left with is the 1. And the 1 is 1 times omega naught. And then you have the same beta as a supertube. So this is why in the supergravity language, the J left and J right are exactly what they were for the supertube. This is sort of obvious once you know the holographic dictionary, because what you're doing with this particular superstratum, the 1, 0n, is you're acting with L minus 1s on the left moving sector of the string. So you're not changing any of the angular momentum. You're just loading up more and more momentum charge. So this thing is a solution which has exactly the same angular momentum as a supertube, but it's got a, in principle, a very large momentum charge being carried by all these modes. Okay, so as I said this. Now, what we're going to do now is start moving towards trying to understand what this geometry looks like. And I'm going to give you a whole bunch of different perspectives on this. But before I do this, any questions? Yeah.
Last question again.
Sure.
So for the supertube regularity condition, we have to have here this term proportional to C.
Yes.
C, if you don't expand into modes, it's just some integral at infinity.
It's a number. It's a number. It may not be an integer. It should be. Well, it will be quantized at some point. But okay. No, this will be quantized. Excuse me. The QP will be quantized. The Fourier modes are free parameters.
Yeah, but for the C, you need to integrate something at infinity.
It's just a convenient way of getting at the coefficient. Where has it gone? C was the RM. Yeah, here it is. Here C was just the RMS value of this quantity.
Yeah, so it's our way of getting rid of the stuff at infinity, correct? When it would be...
It's a way of making it regular at infinity. But if you leave C in the calculation, so when you actually do the detailed calculation, I've used the solution very explicitly. If you leave it in its raw form without doing all this stuff at infinity, you'll wind up with all sorts of terms C in the middle. So these expressions will have explicit C's in them when you start looking at, where is it? This one. The supertube regularity condition, you'll find something, well, you do find the explicit C's in here. So, once you set C to its value at infinity, you then find that it then gets related to this supertube regularity.
My question is, what I'm interested in is, because the supertube regularity condition is something that it's at R equal to 0, and
yes.
and it involves a quantity that we define because we want to make the decay at infinity the appropriate decay that we're looking for.
You want asymptotically ADS3 times S3 and not some other space.
Yeah, so is there any significance to that? The asymptotic decay also seems to somehow be related to the regularity at the supertube.
You see this all over, or you always see this sort of thing, because what you're trying, it's like when you solve the Laplace equation. If you solve the Laplace equation, you can avoid singularities in the middle if you have the thing blow up at infinity, or you can put singularities in the middle if you don't mind, and you make it fall away. So it's always a trade-off when you're solving differential equations. There's often going to be singular behavior that you can move around by adding a homogeneous solution. And that's exactly what we're doing. But we're tuning the homogeneous solution so it's well-behaved in infinity and well-behaved in the middle. And so, but you can always trade this off. But you really want to have something that is, looking like the throat of a black hole. So if I declare my system to be the ADS3 region of a black hole, I can make this also asymptotically flat as well. You find that you have to pick the constants or the homogeneous solutions to get the asymptotic ADS-ness. And then when you go to the middle and say, I don't want any singularities, you find that those homogeneous solutions have to be locked onto other sources. So it's the usual sort of trade-off that when you solve any differential equation, you have to put in boundary conditions of infinity and some conditions about the sources.
Okay.
And, that's where the physics lies. So in fact, most of the physics of this lies in the end of the day in this RMS solution and fixing it to the appropriate boundary conditions. The oscillatory solutions are essential. You've got to work them out. but they don't really wind up driving very much of the actual essential physics. They don't drive any of the asymptotic charges. They don't drive, well, I was going to say, I don't think they drive the regularity conditions except for the coiffeuring constraints.
Okay, thank you.
Yeah. Okay, so now what I want to do is spend a whole chunk of time telling you what this geometry looks like, because it really is the workhorse of this sort of when you want to analyze the basic superstratum. And so what I'm going to do first is write it in a way that separates out the S3 from the thing that looks like an ADS3. And this first step can be done for any metric, but I'm going to separate out what I'm going to call the base coordinates, u, v, and r, from the sphere coordinates, theta, phi 1, and phi 2. But just think of it arbitrarily as I'm just doing some weird shit separation of coordinates. And I'm going to write the metric, and I can write any metric in this way. I just simply write it as only things that involve u, v, and r down here. And then only things, then there are things that involve dy, i's, but there could be mixed terms between this set of coordinates and this set of coordinates. So let me just allow the mixing to be described entirely by some horrible vector field B. And I'm going to, for convenience, take the determinant of this and compare the determinant of this to its value at infinity. Well, it's going to be the S3. So this is the ratio of the shape change S3 to the S3 at infinity. And I'm just going to throw that in there. I'm perfectly at liberty to do that. It just redefines this metric. So far, I have done absolutely nothing except regroup the metric. But you do this for the 1,0n superstratum, and you find there's a miracle. And the first miracle is that this three-dimensional metric, once you factored out this thing, only depends on u, v, and r. In principle, it could have depended on all 6 coordinates, because remember, we got fluctuating modes that depend on phi 1, things that depend on theta. So this metric could have depended on every single coordinate in some non-complicated way, or some very complicated way. But the actual solution, it doesn't depend on phi 2, but okay. But the point is, a miracle happens when you do this. You find that this three-dimensional metric is simply a three-dimensional metric, and it only depends on u, v, and r. Then another miracle. You look at these fibration terms, and the only non-trivial fibration terms that turn up are when d phi mixes with some of the base coordinates through a vector field. And these vector fields only depend on u, v, and r. So you do this thing, and you know, when you look at the metric, when you first look at the metric, you begin to see how this happens, but you look at this metric, and you find that by writing it in this fiber form, it looks it is exactly a three-dimensional metric with three-dimensional Kaluza-Klein fields. And this is exactly what you expect from 2 U1 Kaluza-Klein gauge fields. You want the killing vectors, this is a killing vector, to be decorated or added to by gauge fields that only depend on the base coordinates. So just from doing this game alone, this strongly suggests that there must be some kind of consistent truncation where you can reformulate the theory entirely in terms of a theory on K, and these vibration fields turn into Kaluza-Klein vector fields, and in this case, just a U1 cross U1 theory. And it turns out that this delta is also magic. It's exactly what you need, that if you know how to do your dimensional reductions, when you reduce from P dimensions down to Q dimensions, you always get a power of the determinant of the internal matrix that decorates the lower dimensional piece. And this is exactly what you need. It's exactly the right power. So in other words, this thing is telling you that even gravity wants to reduce down to a three-dimensional gravity. So it looks like it. There's an awful lot of heavy lifting to be done, but the answer is it really is. There is a consistent truncation. This is some work I did with Daniel and Robert and so on earlier this year. And in fact, you can also include what's called the 1,1 superstrata, 1,1n superstrata. You can allow m to be 1 as well and take any linear combination of 2 holomorphic functions in there. And it can be entirely described in terms of a gauge supergravity in 3 dimensions. This was a huge amount of heavy lifting to prove this, but this is a 3-dimensional action. And so, as evidenced by the fact that there's an epsilon symbol. And let me explain what there are. There are scalars. There are 4 of them, chi1 through chi4. These encode the modes of Z4 and theta4. So these are the things that are the seeds of the solution from the superstratum sense. So, and incidentally, if you want to add more tensor multiplets, all you do is you add more chi's in a very particular way that's described in some of Samplaben's papers and so forth, So we know exactly how to add more thetas and chi's to this thing, thetas and z's to this thing. But for us, all we need is this, and these guys encode that. Now, there are more scalars here. These have a very simple interpretation. The scalar matrix MAB and its inverse, the A and B, I should have said, run from 1 to 4. That's their SO4 indices, and it's SO4 gauge theory. And so there are 4 of these, and they transform as a vector of SO4 and all that sort of thing. This is a symmetric 4x4 matrix, and it is, in fact, the shape of the S3. You think of the S3 as being defined by, in R4, and there are Cartesian coordinates, XA, and the sphere is, the sum of XA squareds is 1. Well, basically, the metric is given by MAB contracted into the, appropriately into the 1 forms DXA. So this set of scalars does nothing other than tell you what the shape of the S3 is, and here they are. So we have these guys, Z4, theta 4, we have this as the shape modes, and there are Kaluza-Klein vector fields. Remember, there's an S3. So there's an SO4 rotation group. SO4, there are 6 killing vectors of SO4, and they give you a skew symmetric set of gauge fields. And this is the gauge coupling. Now, there's a little bit of subtlety in this coupling. There's actually some more complicated, slightly more complicated nature of this connection. No, not that, I think, no, sorry, I've got this explicit so that I don't have to worry about this. But anyway, what's happening here is that now we have the field strengths, and there's a Chern-Simons term, which is kind of amusing. And then there's a gauge coupling. And the gauge coupling, as is universal when you do dimensional reductions, it's set by the inverse radius of the sphere. So this really is, this very complicated superstrata, and in fact a generalization of it, is entirely described by a 3-dimensional theory. Now, I'm going to say more about why that's important in a moment. But basically, the dynamics of this is entirely in the UVR direction. The sphere is an auxiliary space that just goes along for the ride, and the magic of the consistent truncation and the heavy lifting that we did in that earlier paper was to show how, once you solve this theory, you've actually solved the 6-dimensional theory, which means you've actually solved and got a solution of 2B supergravity. Okay, and there's of course a scalar potential. And basically, it's determined entirely by the scalars, and the scalars roll around in the bottom of this potential. So and this potential, believe me, I spent my life working on, a lot of my life working on these sorts of potentials. This is a really easy one. Okay, so the message here is that this 3-dimensional supergravity captures all the fundamental degrees of freedom and their dynamics and everything about the 10n and 11n family. It's cool mathematically, but there's a really much more fundamental reason why this is important. But I'm just going to show you where the bodies are buried. So I told you that basically the scalars, so for the 10n superstratum, only 2 of these things are activated. The other 2 are set to 0. For the 11n, you turn these on as well. And then basically the holomorphic function of interest, you learn that the scalar is holomorphic, and this turns out to be the exponential of a Kähler potential, but let's not even go there for the moment. Here's the shape modes. The shape of the sphere is very simple. It doesn't get deformed in this direction, and it gets deformed by the magnitude squared. This is this sort of fact that this warp factor always winds up by 1 minus the modulus of f squared. So it turns the shape of the sphere in an interesting way. The Kaluza-Klein gauge vectors are very simple. This one's actually pure gauge. It's DDT. That's sort of important that it's not trivial. You can trivialize if you like, but there's a reason why you want to stay in this gauge. And then there is non-trivial content in this gauge field. It really does have some interesting field strength. Okay. And then the 3-dimensional metric. So one of the reasons for going to this formulation is it tells you what the 3-dimensional metric really is. And I want to spend a few moments just admiring this form. So remember I said that R and V naturally encode into a holomorphic coordinate. This is the constant curvature metric on essentially the holomorphic 2-plane. So half space, if you like, or the disk, or whatever. Psi, remember, psi goes to 1, or modulus psi goes to 1 is the infinite boundary. So this is the conformal mapping of essentially R2 to the disk. It's constant curvature metric. And notice, I'll come to omega in a minute, and notice, this is just a bunch of constants. This is dt, and this is another set of constants that have everything to do with the background. And this is extremely canonical. This has a complex structure, J. this is the potential A for which dA is equal to J. So this is the potential, electric potential, that gives you the 2 form, which is the Kähler form on this base. And notice there are no warp factors here. It's just constants. So this is an unbelievably beautiful and simple Kähler fibration form. And if you've ever looked at supersymmetric black holes in any odd dimension, this is where you go immediately. Oh, sorry, in any odd ADS. So ADS 5, if you look at the Katowski-Real black hole, it has exactly this form. You have a constant negative curvature space, a non-compact CP, and here it's CP1, non-compact CP2 for Katowski-Real. You then write it as a time fibration using the vector field that you get from the Kähler potential here. That's the starting point for Katowski-Real. And then you deform it, and here's a deformation. The deformation here is the only place where all of this superstrata stuff sits is in this conformal factor. So the metric really is, if you put omega as 1, this is, and just the constants correctly, on the money, this is ADS3. The deviation from ADS3 is entirely in the warp factor of this hyperbolic base. The time fiber remains utterly unchanged, and its potential remains utterly unchanged. So this is an incredibly canonical structure for looking at ADS black holes, and I wouldn't be surprised that there should be some version of this, and this is another research project one to think about, for the Katowski-Real black hole, or not their black hole, but some black hole in ADS5, and, you know, but this is the structure. The minute you start looking for supersymmetric black holes in ADS odd, this is what you should be looking at. And here it is emerging straight out of this, except we have this wonderful magic function that I've proven to you is never negative. It's always positive definite. And it just acts as a conformal deformation. This is what contains all the superstrata stuff. So, as I said, it's a beautiful asymptotically smooth, conformally Kähler fibration. And it's asymptotic to ADS3. It's asymptotic to ADS3 because this dies away and this goes to 1, and there's the ADS3. It's caps off smoothly at xi equals 0 because at xi equals 0, F only starts at first power of xi. So this vanishes, and again, it goes to 1. So this quantity goes to 1 at infinity, and it goes to 1 at the origin. So the best way to think about these things is it's really going back to ADS3 in the cap, and it's going to ADS3 in the intervening in infinity. And in the intervening region, this function has something to say about the deformation. Okay, so before I go back onto the geometry of this, I want to emphasize why the consistent truncation is incredibly important. It's you know, if you like gauge supergravity, it's a thing of beauty, but there's a reason why this is very important to us. What it's done is it's reduced the problem of this set of superstrata to a 3-dimensional action. And that action contains the BPS superstrata and what I'll call the anti-BPS superstrata. So I want to explain what I mean by that. So here's how we started this story. We said, I want to make some particular coherent momentum waves left moving on the D1, D5 system. And it's got 4 supersymmetries, 0, 4, because it's got a certain holistic projection on this D1, D5 direction. I can do a really trivial thing. I can replace y by minus y. It flips the orientations, flips the holistic projections, and I get a right moving momentum wave. And it's got 4, 0 supersymmetry. It's got the other kind of supersymmetry because the holistic projection is the opposite. I call those anti-superstrata. They're just parity flips of known superstrata, and they're completely trivial to generate. It's, roughly speaking, it's the same as interchanging U and V in the whole discussion. So now I'm going to show you in a few minutes how you can localize momentum waves. So what that means is that the top half of this picture has 4, 0 supersymmetry. The bottom half of this picture has 0, 4 supersymmetry. There's an intervening region where they talk to each other and supersymmetry is broken, but these two supersymmetries hate each other. There's no supersymmetry when you put them together. So you can localize the momentum waves in principle and make an interesting setup like this. Now, the point is that you've got to let time run. These things will collide and they will produce graviton modes. That's the nature of the D1, D5 system. These things are heading in completely opposite directions. They will collide and recollide every time they go around the circle, and they will produce graviton modes. But with the whole point about this is because every element is BPS, and because you can if you can separate this mode from this mode, you have a beautifully well posed initial value problem where you can slam these modes into each other. In principle, before we had the three-dimensional truncation, it depended on every single mode. Remember, this is U independent, this is V independent, but together they depend on everything. But the consistent truncation means you can set up this whole problem in three-dimensional supergravity in a way that it only depends on U, V, and R. And so once I've shown you can localize the waves, you can realize that this is true. But more generally, what I want to say about this consistent truncation is that inside that consistent truncation, there are not just BPS things, there are non-BPS things, and there are lots of non-BPS things. And those non-BPS things might be one of the best ways to get at non-BPS superstrata, in fact, non-extremal superstrata. And here's a simple configuration that I know is in the three-dimensional supergravity theory. And it sure as hell isn't BPS because it undergoes what I call the superstrata scattering. So all this to say that we've got a 2B, we start with a 2B supergravity, we reduce to 6 dimensions, then we can reduce to 3. And if you solve the three-dimensional theory, you have a solution to 6 and a solution in 10. And those solutions, there are certainly solutions there that are non-extremal, non-BPS, that look like thermalization of superstrata scattering. So this is why I'm excited about three-dimensional supergravity. It's not because it's gauge supergravity and that's what I wrote my thesis on. It's because it brings within reach the possibility of solving one of the sort of golden problems of this whole thing, the most impressive problem, how to make non-extremal, non-BPS solutions. And 3 variables is, well, numerically at least, just about in the range of doable. This numerically is out of reach. So, and the beauty of the consistent truncation is that it tells you that the degrees of freedom on the sphere are purely ancillary. They go along for the ride, and once you solve this problem, everything else is solved. Okay, so that's preaching to the choir. What I'm going to do now is actually talk about the real workhorse, the one that's been analyzed over and over and over and over again in this game. At least there's maybe a dozen papers about doing interesting aspects of this. And it's the so-called single mode superstrata. It's the thing we first learned how to do. Because single modes are very, very easy. All there is the RMS version. So the important point is in single mode. Yeah, sure.
Nick, sorry, can I ask a really stupid question about the previous slide? So you have these momentum waves going around the circle, and once they collide, do they also again separate again to these different localized BPS modes? Solution that oscillates between being BPS and not? I'm confused.
Okay, okay, let me try and clarify it. So this is meant to be a heuristic picture. The outcome here depends on the strength of G string. If G string is tiny, then they'll pass through each other and they won't notice each other, or very little. If G string is large, then this becomes a very complicated morass and maybe they don't pass through each other. So everything depends on the value of G string. And so, but the sort of picture I'm trying to sell you here is there's a big long backstory here, which since you asked, I should mention. About a decade ago, we started thinking about how to do non-BPS things. And then there was this sort of Goldstein method. Goldstein came up with this interesting method where what you do is you basically put together BPS things into the solution, but you somehow weakly break the supersymmetry using the geometry. And one of the ways we learned to do this after Goldstein was to say, let me put over one side of the universe some pieces BPS, and another side of the universe, something that's also BPS, but anti-BPS. It preserves a different set of supersymmetries. And if I keep them widely separated, that solution is almost perfect, except there's a tiny bit of supersymmetry breaking. And so what I claim is that this is not going to be a solution to the full equations of motion.
Okay.
But it's going to be very close to it, because so long as these things are localized, they're not going to talk to each other, and the error is going to be controllably small. But what I believe is that you've now got initial data for a scattering problem that is extremely precisely posed, that you can set and run and then watch this happen in real time.
Okay.
But the other reason why I want to say this is also to emphasize the fact that everything I've said up until this sort of lecture is really about the BPS story. And we've been building BPS, but I finally got to a three-dimensional action which puts us in the shooting distance of being able to solve stuff. And it contains all sorts of non-BPS stuff as well. In particular, it contains this configuration. And it should contain this process or a version of this process. So, you know, it's possible that this collision could just produce a black hole. Now, let me refine what I mean by that. If you do this in three-dimensional supergravity, it could produce, well, actually, I think if you make this small enough and this big enough, it won't produce a black hole but if you make, so one way to approach this problem is make this small or nearly perturbative and make this a huge, great soliton. Then I think it won't necessarily make a black hole. But when I say make a black hole, you have to unpack what I really mean. See, gauge supergravity is kind of a Faustian bargain. You sell the soul of the problem in order to get solvability. What I mean by selling the soul in this thing is that you have basically restricted the degrees of freedom hugely to get it to fit into this three-dimensional supergravity package. But by doing that, you've got a much more solvable system. And what you may find is that much more solvable system says, oh, it's going to make a black hole. And then you realize that maybe because you sold your soul by packaging it three-dimensional supergravity, you have suppressed all the degrees of freedom it needs to have in order to do something other than be a black hole. And this is the sort of meta, there's a meta argument here, which is the sort of what Joseph and I typically have with, you know, Harvey Rial and people and who do GR. You know, we don't fundamentally disagree, but Joseph and I take the perspective, if you do things in string theory has so many more degrees of freedom that it will resolve any singularity that GR tries to make by turning on string modes, by turning on fluxes, by going through geometric transitions. So the sort of whole backstory of microstate geometries and fuzzballs is that there's a huge number of degrees of freedom in string theory that can resolve singularities and remove horizons. So whereas in general relativity theory, you know, you slam two things together, all it can do is make a shock wave or a black hole or something. And that's because general relativity theory has far too few degrees of freedom to avoid singularities. So here, I might be making the same error. If this makes a black hole, it doesn't necessarily mean the whole microstate geometry program is dead. It just simply means that this three-dimensional supergravity doesn't have the degrees of freedom to resolve the black hole that you just made. But conversely, if it doesn't make a black hole, you've finally got a non-BPS microstate geometry. Right. And if I had to bet, I'd say that if you made this a honking great big soliton, and this one too, it'll probably form a black hole. But if you make this a modest to small anti-momentum wave, and this is a big heavy thing, it will slam into each other and they will produce a lot of gravitational radiation. And in the ADS3, it will go into equilibrium and it'll slop around, but it won't be a black hole. It will be some other microstate geometry with a whole bunch of excited gravitons in it. That's what I hope anyway. But this is, I tend to believe that once you've got a big piece of topology, a smallish perturbation can't destroy it. Well, if you take two pieces of topology and you collide them with each other, now, when I'm saying this is a big, fat piece of topology. And if you stand them together, yeah, okay, all hell might break loose. But if you take this guy, a big piece of topology, and whack it with something a bit smaller, the topology will reassert itself. This will dominate, but there will be a sea of this sort of stuff. But this is for me, this is, I think, a really cool problem, and it's getting within reach of numerics. And it might, the other thing that's really important here is, we do have non-extremal, non-BPS microstate geometries, JMART, and there's some stuff there's some these bubbles that Guillaume and Joseph and so on, and the people at Ecole Technique have been making. They're really cool, but they're really outlier states in the holographic dictionary. Whereas these states are left moving momentum waves, right moving momentum waves. We're colliding Strominger-Waffer microstates. These are right in the center of the typical sector of the theory. And they are, things for which we have really good faith that these are not outlier black holes. These are real, this would be a very low temperature, but non-zero Hawking temperature black hole. And this would be an honest to God microstate in that thing. So you're right in the center of where you want to be rather than being in some extremely highly spinning outlier state. That's why I think there's another reason why this is exciting. Also, another reason why this is exciting to do is we know exactly the holographic dual of this process. We know exactly what this is in CFT. So in principle, you can calculate this process in the CFT and compare it. So if you're very strong, there's probably some precision holography to be done to check this. So, you know, it's the best possible world in the sense of, because we've done so much precision holography of these states, this is going to be hard, but we can check if we can do this, we might be able to check it against holographic calculations. So for me, this is currently, you know, there are many ideas about getting at the non-extreme or non-BPS microstate geometries. And I think this is one of the more exciting ones because it puts you in a place where you know the dictionary, what the holographic dictionary is, and then gives you the chance of testing it. Wow, okay. So any other questions? I should probably not impose on you too much longer. Okay, so I want to just tell you about the simplest case, which is single mode. And this actually has the beautiful fact that makes life a lot easier because you only get the mod, it's one mode. You pick your favorite mode, N, and you run with it. The point is the magnitude of F doesn't have any phase dependence. It's an example of what's sometimes called the Coleman trick, where you basically have some interesting modes that depend on angles in some way or depend on time, but the metric only cares about the modulus squared of them, and then the phases all cancel out. And you get a metric which looks exactly like this, and you're supposed to see it looks an awful lot like ADS3. Here's the time vibration and so forth. And then there's this function here, F2. And similarly, the three-sphere. Here's it's easy to write down what this thing is. It's basically, as I promised, it's d theta squared, sine squared theta, cos squared theta, and here are the Kurzweil-Klein vibrations. And then there are all these crazy bump functions. This is the omega hat we saw before, and then these lambdas. And then I've packaged this parameter in this way. So basically, this is the geometry that you see in all these pictures. The regularity condition is just there's only one momentum mode, and I've called the single mode B now, yeah, B psi n. And so basically you get the regularity of the angular momentum is exactly what I said it was, and so forth. And you get this geometry. And I want to just say what this geometry looks like. First and foremost, it's BTZ up until this point. And then, so basically you have an ADS3 region, and then R is of order root NB, but you look at this and you realize that R is of order root QP up to factors of root 2 that I don't care about. And this is exactly the transition of BTZ. You start with ADS3 and then it transitions from ADS2 across S1 throat at around about where R hits the value of the momentum charge, the square root of the momentum charge. Now, all the other interesting stuff starts happening here. And if you look at all these bump functions, it doesn't take long to convince yourself that they all do something interesting around about R is root NA. Basically, this one, for example, as R goes to infinity is 0, and as R goes to 0 is 1, and that rapid change occurs at R is root NA. Similarly, all these bump functions do something, they go between two different constant values, and then basically they do that change around about that region. And that's this zone which we call the locus of the superstrata mode. It's where the transition to the cap happens. But put another way, if you sit up here and put a Gaussian surface and measure the momentum charge, you'll measure QP. If you sit down here and put a Gaussian surface and measure the momentum charge, you get nothing. This is where the momentum charge is localized inside the solution. Okay, so just to sort of give you the geometric features of what we have here, for R greater than root NA, up here, you basically get B2C. For R less than root NA, remember I said it caps off smooth at R is 0. It's actually ADS3. So this is perhaps not the best depiction of it, but you have an ADS3 region here, an ADS3 region here. Now imagine you just cut out the bowl of the ADS here and put it over here and then connected it with a vertical piece of pipe. That's pretty much what's going on. Down here, it's on the money ADS3 again, albeit a small piece of it. But that's what I said when I said before that basically the warp factor goes to 1 at infinity, the warp factor goes to 1 at R is 0, and the warp factor in between is what creates this. Okay, and there's lots of other facts I want to just mention about this, and I've just been cheating, I've taken it out of the lecture notes. So I've said this, the bump functions are localized there. Now, The other parameter is the difference between here and here, B and A. And B over A controls the length of this ADS2 throat between the cap, but also it controls the redshift factor between here and here. So B over A is perhaps one of the most important parameters in the superstratum. It's also the relationship between QP and the angular momentum. So A controls J left, and this controls QP. So how much QP you've got compared to angular momentum. And if you put A as 0, you just say 0, you wind up with the BTZ metric on the money. So this is a sort of singular limit of the superstratum, but it is exactly extremal BTZ. But to have a smooth cap, you've got to have A positive, but there's a minimum value. It's controlled by J left, and if you quantize J left, the minimum value is half. And if you do that, you find a huge redshift between here and here. Now you can ask the question, suppose I put the lowest energy excitation I can put in the cap. I imagine a wave going one wavelength across the cap. And then I ask, what's its energy measured from infinity? So it depends on the scale of the cap and the redshift and so forth. You compute it, and you get the right gap energy for the CFT. On the money, you get the correct energy for the dual CFT in the maximally twisted sector. And as I say, the holographic dictionary for this geometry is well known. So this is the workhorse. This is the reason why this is an exciting geometry. There's one more reason, which makes it also very interesting, and in its own right, maybe I should brag a little. The referee, when he saw our paper, said, this paper is interesting enough, the fact that it has a separable wave equation, let alone its interpretation in terms of microstate geometries. In other words, it's already cool to get separable wave equations. And if you take the 6-dimensional geometry of the 1,0n single mode superstratum, and you look for the 6-dimensional wave equation, it separates. And so what happens is you get this radial stuff and this sphere stuff. And moreover, all the interesting physics is buried in one of these bump functions. And this is completely trivial. Even though the sphere is changing shape and size, the Laplacian you get, the inverse metric on the sphere, is that of the round sphere, and it's all Jacobi polynomials. So what this means is, let me come back to that. What this means is you can solve the wave equation in this background, and you can analyze all its modes, massless wave equation. The massive one's doesn't work. So you can probe the hell out of this geometry using wave equations. And so, Joseph and Pierre and Rudemont and I did that, and so Raju and so forth. There's been several papers doing this kind of game. The other reason that's interesting is separable wave equations also imply integrability of the null geodesic problem. So therefore, you can do all sorts of wonderful things. And so this class, the single mode 10Ns, have become perhaps the most studied of all the superstratum, and they are relatively simple. And their wave equation, this is the wave equation of ADS3, this wave operator here. This is the decoration that comes from the superstrata through this bump function. This is complicated, and you need to use WKB methods to understand it, but all the interesting physics is in this term, and in particular this thing here, this bump function. Okay, and I wanted to mention a couple of others before just concluding. The single mode superstrata are interesting and they're nice, but they have the momentum wave smeared around the Y circle. And I've already said it's kind of cool to try and localize them, and we can do that. And this is my favorite localization. I think it was Daniel who came up with it. This is the best one to use. Basically, what you do is, here's my holomorphic function. There's some stupid normalization constants that I don't care about, but it's psi over a constant, forget kappa. You can, that's a pure phase. Kappa is real. So what happens is that it's looking like it wants to make a pole when psi is e to the gamma. But if you take gamma bigger than 0, this is bigger than 1. And remember, psi is less than 1. So it never makes a pole, but it gets big and peaked. And so what you can do is, by choosing gamma small, you can make a very sharp peak. And so gamma is 1, you get a little peak, and then you make gamma 0.3, you get a very sharp peak. So that means you can really localize the hell out of the momentum density. This is what controls it. And so you can write down the metrics and start looking at contour plots of the size of the Y circle. For this is gamma is 1, this is gamma is 0.3. And you see the metric over here. It doesn't even know there's a momentum wave really lurking. Here it knows a bit about it. But you can really localize the momentum in one region of the circle. And by adjusting kappa, you can move it around. So you really can, with these Cauchy distributions, realize this idea of localizing a momentum wave on one side of on one part of the circle and not on the other.
So this momentum, Nick, sorry, if I, in the geometry, where can I think about this blue place, the blue place?
This is
it the center of space?
No, this is the Y circle, and this is at infinity. The center of space is right here.
But so how can the momentum be localized at infinity? The momentum needs to be in the deep infrared, otherwise you don't get a long throat.
Let me just see. I'm trying to remember. This is all of xi, but okay. So remember, this is only a piece of the plot. This is the size of the Y circle. And so what's happening is that well, actually, it's not even the size of the Y circle. It's GYY. It's one of the metric coefficients. And so what you're supposed to see, it's very hard to draw the picture of the full metric, but what you're supposed to see really is you can localize the effect of the momentum wave in some very narrow region, and then GYY remains basically constant in the other region. So it has no knowledge that there's this big lump of momentum that's going there.
I see. But the momentum has to be at the origin of the space, right? I mean, that place, I think, is the origin of the space, right?
So what indeed, what happens is, so let me put it another way. Xi runs from, R is infinity, psi is 1, and R is 0, psi is 0. So this momentum wave actually localizes, let's see, it goes to 0 at the origin. So therefore, this is ADS3 again, right in the middle. And then what happens is that this thing has a bump or a peak, which you can localize on the circle, but then of course it diffuses into the solution. So at infinity, it's all here. It's this big spike is this spike here. But then as you go in radially, it starts to diffuse, I guess, into some kind of entanglement wedge or whatever. But it does diffuse in the solution, and this is a fairly coarse-grained plot. So it does make its presence felt. But what we've done is we've really pumped it up and put it at infinity. This is infinity. We've localized it hugely, but then it diffuses into the solution by the time it gets to the middle. So I would imagine with the left moving and right moving guy, you would start off with a little localized bump here, a little localized bump here, and then in the middle, all hell will break loose. But what you're supposed to see is that this momentum is diffusing into the solution, and it's not changing very much at the bottom here. It's creating the usual superstratum solution with an ADS3 cap, and but at infinity, I managed to localize the hell out of this momentum wave.
But it's not at infinity. I mean, this is the thing which is confusing me. I mean,
infinity. No, this is Xi's infinity. Size 1 is infinity.
But is there some other integration going on here? Isn't there like some time coordinate that you have to integrate? Or
oh yeah, look, we spent a lot of time trying to figure out how to represent the localization, and this is the best we could do in this paper. All we did was we plotted one of the things, part of the metrics that's extremely sensitive to the momentum wave, and it's the size of the Y circle. So coefficient of dy squared, with some factors removed that are just boring. And so yes, all sorts of other things are happening in the metric, and there's
But if I'm to plot this in your previous picture, the one with the indecent-looking superstratum,
so
where is this place? I mean, normally the momentum wave gets local. If you go to your previous slide, the one with the superstratum picture,
colliding.
No, there. Stop. There. This perfect. So there's a superstratum mode.
What's happening is that you've localized it up here. You've now got the momentum wave highly, highly localized. So you
don't have an ADS2 throat at all.
You do, but it's a really weird shape. But it does reassert itself. When you get down to the bottom, let's call this the normal cap.
Yes.
And so what actually happens is you start off with a wave up here that's highly localized here, and then you get some really weird, wild shape here. And then that really weird, wild shape, as the momentum diffuses into the solution, it reasserts itself into a nice, smooth, round cap that looks like this. And that's sort of, I think, what is being depicted here. Let me get through. So what's being depicted here is that you have some very, very localized momentum wave, but by the time it diffuses the throat, it's ADS3 and there's an ADS2 throat and all that sort of stuff.
Actually, where do you see the ADS2 throat at all? Because there shouldn't be any ADS2 throat at all. ADS2 throat only happens when the momentum is localized at the very bottom.
I don't know.
Let me just band you had in the previous.
I suspect that. Okay. To be honest, Joseph, I haven't thought about this more deeply than this, but basically what I've got is the momentum charge localized here, and I see as I go, the magnitude of psi is the radius. As I go in, I start seeing that it smears out and localizes, it delocalizes. because what's happening is this momentum influence is spreading out. This bump that I made at infinity is now shrinking to probably to look more like this, because as you start dropping psi away from it being near 1, this function is now it's no longer peaked. You know, if magnitude of psi is a half, the reason why it's peaked is because this is nearly a little bit more than 1. And if you get close to this being a little bit less than 1, then this is a huge peak. But when psi is a half, this is a half in the bottom, this is a half in the top, this is a number of order 1. And so the peaking is really a feature of what happens when your magnitude of psi gets near infinity, and then that peak diminishes as the magnitude of psi gets down, and this just becomes a rather uniform, boring distribution of momentum wave. So I think of it, the way I sort of, when we read this paper, the way I was thinking of it is you've peaked the momentum wave, but as it falls down the throat, or the charge evolves down the throat, it diffuses out and creates smooth geometry. I think that's the way to think about it, but I think Robert was here. I don't know whether he wants to add anything more, because he and Daniel were more responsible for these plots than I was.
Another thing to realize about this is that this is G tilde YY. There's another there's another factor here, which, so this is the bit that is sensitive to when you vary this function f. There's another piece which imposes the overall throat-like geometry.
There's the redshift function, which I've thrown away. The thing I was calling omega hat before has been thrown away on this thing. So, you know, all this, all I wanted to point out is that one of the driving forces between this holomorphic formulation is we wanted to think about things that weren't smeared uniformly around the throat, but were localized. And the reason why I wanted that was really because of this idea that you might be able to do some almost BPS construction. But it's still cool to be able to do holomorphic variables. But Robert or Daniel, do you have anything more you want to add?
When you do the integral to figure out the momentum charge around the boundary, this modulus of f squared thing, this is really the thing you have to integrate. So it really is the charge density. Yeah.
But that charge density, I can imagine taking the Gaussian surface and lowering it down. And so the question is, where, you know, I know in the single mode exactly where it localizes. It's that R is order root n times A. I haven't actually looked to see what happens if I imagine trying to sample the momentum charge at various heights in the throat.
What happens if you do a contour plot of F as a function of?
That's a good question. I don't know. to be honest, I don't know. It's actually the contour plot of the modulus of F squared. So you just have to integrate this. Actually, it's a little bit more complicated. The momentum charge is a derivative of F times F bar, essentially. And then you integrate it around psi, and you pick up whatever residue it is.
But isn't the momentum charge also the sum of the Fourier coefficient?
Yes, so do that. Actually, it's the sum of n times the Fourier coefficients. The n reflects the fact there's one derivative.
Yeah, okay.
So just expand this in a Fourier series and you'll sum it up. That's the momentum charge measured at infinity, but if I tried to localize it, I could imagine trying to do that contour at different places on the Y circle. I'm not sure what will happen if you do that, but I believe that it still makes a very deep throat. So I believe this is still a deep superstratum. It's just that you put the momentum charge at infinity in a very local place, and then you're letting it diffuse out. So this is perhaps a picture. You see, as you've got a less peaked one, but you see what happens. The influence of the momentum charge diffuses out as you get to near the bottom of the throat, and there's the ADS3. So whatever the momentum charge is doing, it's being slowly diffused out as it goes into the throat. These are all good questions. I don't know the answers to them. Let me finish. I've got a couple of concluding slides. Sort of trying to make conclusions and suggestions about interesting problems and so forth from these lectures and just finish on that. So basically, there are so many open problems, and I just wanted to summarize or just reiterate, my Carthago delendum essay kind of statements, the sort of broader perceptions. the one unsolved problem we have here is the twisted sector states. We do not know how to make coherent collections of twisted sector states. There are one or two little examples which we wrote a paper on, but trying to get a coherent statement about coherent combinations of twisted sector states look like. All the superstrata I've discussed are untwisted sector states in the holographic things. The other thing also is that the holographic jewels of multi-centered solutions are not known. Now, if you have two unknowns, one in supergravity and one in the ADS CFT, it's tempting to think that maybe the two unknowns are actually the same thing. Now, that's a pretty poor argument, but there are indications that maybe the multi-centered solutions might be somehow connected to this issue of coherence twisted sector states. And let me just put it in as sharply as I can in terms of the holographic field theory. In the holographic field theory, you've got something that's asymptotically ADS3. And that's the C is equal to 6M1N5 conformal field theory. It's the conformal field theory of the D1, D5 system. In the middle, if you have a multi-center solution of this, when you go to the infrared, you find a multi-center solution that is smooth, it's got fluxes, it's got stuff. Holography tells you that this must be an infrared phase of the original UV D1, D5 CFT, and that the fluxes should be order parameters of that phase. So there has to be an interpretation of multi-center solutions as some kind of phase of the D1, D5 CFT. What is the phase? And it's tempting to suggest that, and we've got sort of heuristic arguments to suggest that maybe it's some condensates of these twisted sector states, but it's really an open problem. There's another set of interesting things that happen with the multi-centered things, and it's also stuff that you see that Sean, I think, has done work with Samir on, about lifting of states above the ground, index states and how they lift if you change the moduli and so forth. And CFT calculations show the lifting can be actually rather modest. So how does this sort of lifted states be thought of in terms of black hole microstates, and what does the lifting that Sean and Samir have studied look like in the holographic dictionary? I think that's an interesting sort of set of questions. I won't go too much more into it. One of the other things that sort of come to the front since I wrote this paper with Emil was tidal effects, scramble and trap infalling matter. What is the CFT dual of a tidal force? What does tidal scrambling look like in matter in the CFT? This is something we're starting to think about already too. There are many probes you can do on these microstate geometries. So far, what's been done in terms of probing the 1,0N superstratum is that we have looked at scalar wave scattering off it. We have looked at geodesic infall to see, and we've looked at, in particular, strings, or also strings on geodesic infall. And we've seen large tides, and we've seen the effects of large tides on the strings. But there are so many other probes that string theory gives you. It might be cool to try something else. But there are very many things you can think about doing, but you really want to think about the one that's interesting to do. There are also stuff, this is a point that Emil has made with great force, is that there are regions in the moduli space of these superstrata where, say, for example, the superstratum starts coming, the underlying supertube may come very close to itself and maybe come close to intersecting itself. Or you can imagine superstrata having, multi-center solutions where some of those bubbles get small. That usually indicates that essentially there's going to be some new low mass excitations that come from the result of that near intersection of supertubes, or from certain bubbles getting small, or very high redshifts causing the cost of bubble excitations to be very small. And then you'll get condensation and new states and new low mass excitations. And there's this beautiful paper from several years back from Ben Niehoff and Emil about W brains. There's possibly some really interesting new low mass excitations that can be studied in coherent phases. There's a question I was raising more generally in my superstratum discussion, which is, it's possible that if you chuck too much matter into a superstratum, it could look like it destabilizes and it goes somewhere else. And if you believe Eperon Santos Real, or whatever, these instabilities lead to Eichelberg sexual shockwaves, but Andrea and Ben Michel and so forth have argued, and I can't remember the third author, maybe it was Don, have said, no, it's just going to scramble into more stringy states. So, you know, the whole point of the fuzzball microstate geometry program is to say, whatever instability you produce, it's going to scramble into stringy states. It's never going to produce a singularity. But it still remains to really interesting question is if you see something that looks like an instability, what are its endpoints? How does it scramble? What does it become? So those are the sort of broader ones. I've got some more technical ones, which are just, you know, I think things that can be addressed more directly. Construction of superstrata on hyperkähler bases in general. If you've got multi-bubble solutions, you can in principle put momentum waves on all of them. Do these modes interact? Do they influence each other? Can you just put, you've got bubble 1 and bubble 2. Can you put superstrata on momentum modes on each of them independently? We also know from our friends who do linearized analysis around these things that there are quite a number of other moduli that we haven't exploited or integrated up. There are metric deformations that can be made to the in the R4 that give you different kinds of moduli that you could excite and perhaps put momentum waves into. The other thing that right from the first lecture I said, we're never going to do V-dependent base metrics. It's unknown territory and it's probably a very difficult problem. So there are, even within the realm of what we know how to do, what I've been discussing, there are lots of new things you could try doing. This one is really hard, I think, V-dependent base metrics. But I do have a feeling there should be some simple things. So let me take an example. Suppose I have a two-centered Gibbons-Hawking solution, or if you like, I have just a single bubble, the superstratum. There are going to be things that look like breathing modes. So the scale of the bubble is always set by a balance of the contraction force of gravity versus the expansion force of the flux. You can imagine displacing the size of the bubble. You can displace the Gibbons-Hawking points and then letting them go. Then it should oscillate in place around about that bubble. So in other words, there should be some fluctuating modes which involve the bubbles oscillating in size. And this whole V-dependent base vibration metric might be, there may be some BPS examples in that class, but it would involve V-dependent metrics because you're changing the shape of the metric as a function of V. Again, I mentioned a few of the probe calculations in these lectures. There's lots of ones out there that are probably fairly easy to do. The questions are really interesting ones that will teach us something new and different. More ambitious is, okay, you drop a probe in. Can you do anything with back reaction of that probe? Can you sort of see how maybe there's some energy transfer to the background? In particular, these microstate geometries have big moduli spaces. You know, you can, rather than turning on 2 Fourier coefficients, you could imagine that some interaction will generate a 3rd Fourier coefficient. That's a modulus. It doesn't change the momentum charge, it just reshuffles it amongst excitation modes. Or you can imagine that there are actually true moduli which just are unperturbed, and you could imagine maybe throwing a probe in and it will create some slow motion on that moduli space. And finally, the really most important one is we really need non-extremal microstate geometries. I've said that I've described one way of doing it, but there are other ways of doing it. One of which is to look at things with large moduli spaces and look at putting the centers on slow adiabatic motions. Another which is an idea that Joseph and Bogdan and I have been talking about, which is taking fluxes and balancing them so that you make an anti-flux and a flux on 2 different bubbles and seeing if by symmetry you can balance them like balancing a pencil on its point. It will make a solution, and it only exists because of a high level of symmetry. But even if you make that solution, you can then speculate about how it decays. Anyway, this I think is the highest priority at this point. Trying to find any good ideas, and this will be really, really highly appreciated, and any progress would be fantastic. So let me just finish with the last and final thought. Really, from my perspective, the best advice I can give is really to find the calculation. There's lots out there to do that's just within your reach, and it's going to teach you as much as you possibly can about black hole microstructure. And I'll leave you with that thought and shut up. Okay, questions, guys? Wow, there's still 14 of you left. I'm impressed.
I have a question that I just didn't ask during the...
Sure.
On the 3D formulation.
Yep.
The asymptotics there are ADS, correct?
Yes, you can. It seems, I don't believe you can get a three-dimensional formulation if you make it asymptotically flat. I think it's critical that it's asymptotically ADS.
Mm-hmm. So when you were talking about possible collisions of momentum waves,
yes,
when they scatter,
yep,
stuff like there will be some radiation. That radiation then will eventually come back.
yes. So and then it will probably settle down. So apropos of this, at some point it should settle into a time-independent state. And that time-independent state, if the anti-superstratum is very low, is weak, I'm pretty sure that that state will be another superstratum, perhaps a little bit more shallow, but with a graviton gas sitting in it. That's the kind of thing I think. Some kind of fundamental superstratum state, but with some time-independent soup of gravitons. And it'll be non-BPS. So there might be a really interesting class of things that you could look for, which are time-independent final states of whatever that collision produces.
Mm-hmm.
I'm not sure how to, I know exactly how to set up the boundary data and the initial data for the collision I'm advertising. I'm not sure immediately how I'd set up an appropriate solution to the problem or set it up so you could find the final state of that process, because I would guess, and it's only a guess, the final state is a kind of like a superstratum geometry, but with a graviton gas in it. But that makes it kind of interesting to try and look for a graviton gas inside something that looks like a fairly deep superstratum geometry.
Okay.
There are, as I say, I'm willing to entertain any way at getting at non-BPS, non-extremal cases, because I think that's probably the number one problem at the moment. There are lots of other cool, interesting problems that you can learn about in superstratum and develop the theory, but I just really want the answers to or beginnings of examples, even a toy example of a non-BPS that we can play with. I want to see Hawking radiation, because, if you manage to make the thing I just said, which is something that looks like a deep superstratum geometry, but with a graviton gas sort of sitting there in some ground state, then you can couple it to flat space. And if you can couple it to flat space, you can do the WKB calculations, the tunneling process, and how that graviton gas finally leaks out and creates Hawking radiation.
Where are you imagining exactly that the graviton gas will be sitting in the bottom of the cup?
Well, it's in the ADS, okay? So there's an ADS, and presumably the wave function of the graviton gas will decay quite strongly as it gets further out into the ADS. It may be massive graviton gas, but it should be essentially. Remember, in ADS3, if it has a non-trivial angular momentum mode on the S3, it's massive from the perspective of ADS3. So that means the ADS3 wave function is going to fall off as some power of the angular momentum.
Okay.
So therefore, at some point I can say, okay, the graviton gas is dead, and now I can try putting it back into 6 dimensions, coupling it into flat space, and having coupled to flat space, I'll get a nice long barrier, which is the ADS3, and then I'll get a decay on the end of the barrier, which will give me a tunneling into R5, R51 or R41 across S1 or something like that. So I could try and make it tunnel. Ideally, we will have developed superstrata that are asymptotically R31 times S1 times S1. And then we can actually look at it decaying into actually 3+1 dimensional space. This is a house of cards I'm building here, but I think the one that's in reach is to try and do something non-extremal, non-BPS in this ADS3 supergravity. And as I say, the ADS3 supergravity, actually I didn't mention this, but for those of you who might like gauge supergravity and consistent truncations, I think there's another example of this. Some time ago, we showed that the 2-1N superstratum, Robert's actually written more detail on this, but the 2-1N superstratum will consistently truncate, 2-1N superstratum, single mode, goes down to 5 dimensions. You can compactify it on a circle and it goes to a 5-dimensional theory. And that 5-dimensional theory is got a near horizon region, which is I always get this wrong around. I think it's ADS3 times S2, or maybe it's ADS2 times S3. Anyway, it's ADS3 times S2 because it's a ring. But I believe that there's a consistent truncation of the 5-dimensional theory down to a three-dimensional gauge supergravity convectified on a two-sphere. I think the 2,1n superstratum has that property. I think there are more consistent truncations out there. I think there's a paper which is very suggestive, written by Nicolai and Henning, Sandleben, where they suggest that perhaps there's even a consistent truncation of all modes of the superstratum. They don't put it like that, but I can point you to the paper. So there's a lot of formal and amusing problems in sort of the supersymmetric side. And I mean, you know, as I say, one of the interesting ones is to particularly try and do the more general hyperkähler bases. That would be really cool. But any other questions, guys? Any other comments? Robert or Daniel, you've been very quiet. Sasha, anybody?
I have no comments.
Question, any other? Yeah.
Nick, I have a question. So about this, the 10n, it interpolates between ADS3 like infinity and ADS3 down at the bottom. So I presume there is some interpretation as a RG flow in the holography side of this.
That is also a really interesting question too. Yes. Okay. So there's a simple way to say this, but I think the broader set of questions, this broader question is really something near and dear to my heart. So what's going on here? At infinity, you just have the, you know, the ADS3 of the supertube. You've got the D1, D5 CFT with central charge 6M1, M5. And what you're doing is you're making a particular momentum state of that theory. And so it's a state. So a state of a theory has a normalizable, corresponds to normalizable modes when seen at infinity. So what you're doing is you're turning on a particular set of normalizable excitations that creates a very particular CFT state. And so it's if you want to think back to the old stories of, say, ADS5 and N equals 4 super Yang-Mills, this is kind of like the Coulomb branch of that theory. So rather than actually being an RG flow per se, you have the original theory, but you're creating an infrared state in that original theory. You're not turning on a mass, you're not flowing to a lower central charge theory, but what you discover in the middle is that you have a particular state in that conformal field theory.
Mm-hmm.
Now, I think the multi-centered guys may actually be a much more exotic form of renormalization group flow, because you can imagine doing the following. I look at say a two bubble solution. I can turn on flux on one bubble, I turn on flux on another. As I go to infinity, I've now turned on a more complicated set of order parameters, and it should be a more complicated state. Now, this argument is very dubious, and I'll explain what it is. But if you imagine that one of the bubbles is very small, one of them is very large, you can zoom in on one of those bubbles. You can say, okay, that's got some flux. That's a two-center solution. It has an interpretation as a CFT, but it's a CFT with much less flux. So it's got a much lower central charge. So the sort of crude picture I have of multi-centers is each bubble should in some sense feel like a CFT in its own right. And as it connects to another bubble, it should be a coupling to another CFT. And so I think the multi-center solution should be something like a tensor product of CFTs of less central charge, all interacting through their connection point. And so that goes much more in the direction of perhaps a non-trivial renormalization group flow, where you're actually reducing the central charge of the theory and not merely discovering a state within the same theory. So that's the sort of thing that I think is going on here, that it's more akin, well, not more akin, it is exactly what we discover from the precision holography, that superstrata really are flowing, but to a state, a very particular state in the CFT. But you haven't destroyed the CFT; it's still there. You haven't reduced the degrees of freedom. It's just that the infrared contains a very particular state of the theory. So there is an interesting set of questions, exactly about what those holographic renormalization group flows do. But in this particular case, it's a relatively mundane thing. It's a more sophisticated version of the Coulomb branch flows that we saw a decade or almost 2 decades ago in Yang-Mills theory. It's just that this state is a much more, is a smooth, beautiful momentum state that we know exactly what it is.
All right, thanks.
You're welcome. Any other questions or comments or issues?
I have one. The other day, I think we were talking about this. I guess this V dependence on the centers. There was some relation to this potential that you in the 3D super.
Okay, this is an idea that sort of has been in my head for about ever since Joseph and I first started doing multi-centered solutions, and it's simply that this is really about the other set of lectures, right? If I have multi-centered solutions, I have fluxes on bubbles, and then when I tell you what the flux and the bubbles are, it produces a set of constraints called the bubble equations that tell you where the centers, the given Hawking centers, want to sit. And I've always thought, based on probe calculations, that it seems that those bubble equations are really a statement about where is the minimum of a particular superpotential, or where's the critical point of a particular superpotential. So I say superpotential because it's supersymmetric, but you can put it more mundane way. It's where's the minimum of the potential of a potential. And so those bubble equations that determine where the given Hawking centers are really are, I think, a statement about what is the potential felt by moving the Gibbons Hawking points around to different points in the space. And all they want to do is relax down to a ground state where they sit at a certain distance apart from each other. But if you move them away, they feel a force. It's not that it breaks the solution. I think there's a non-BPS solution where you simply move them away. And then you ask what happens? Well, they fall back and they probably oscillate around where they want to be when they're supersymmetric. And so my naive thought was, well, okay, first and foremost, this sounds like a very non-BPS thing. It's time dependent. But I could imagine a situation where, I know that there are BPS solutions where the metric is V dependent. So maybe I can make a left-moving wave out of this oscillation so that this oscillation only carries left-moving momentum wave along the D1, D5 direction. And just maybe that's BPS. But in general, if you kick a system and just make it oscillate around about a minimum, that's going to be non-BPS. And it's going to be non-BPS in a pretty mild way. And that's one of the things I mean by sort of slow motions on moduli spaces. This is quite a moduli space because it curves up. It's a minimum of potential, but it's still a small perturbation of a known BPS system. And naively, if you'd asked me a long time ago, I'd say, oh, that's non-BPS, but it's an interesting non-BPS. But the fact that there are metrics that depend on V suggests that maybe, and they're still BPS, that maybe you can do this oscillating center thing in a way that's still BPS. I have no idea. All I know is that V-dependent base metrics are really hard. And so I don't know, really hard is not the right way to put it. I haven't had a good idea as to how to crack the problem, and there's probably some clever way in. Okay, so all this to say, when you get down to 3 dimensions, I was conjecturing the other day that scalar potential might contain some of that, precisely that information about, okay, remember I said that the matrix MAB is the shape of the 3-sphere. So if I let the scalars that in MAB fluctuate around about their minimum, that's changing the shape of the S3 in a way that could replicate this moving of Gibbons Hawking points. So if I had to find a toy example of this that might just do it, is I go to that potential and ask, are there any interesting motions where, if you look at the potential, the ADS3 times S3 sits at a minimum of that minimum of the potential. It sits at a critical point of the superpotential. And so maybe there's some non-BPS or BPS oscillations of that potential. I don't know, but it's an interesting open question to see what's out there. I'm certain there are going. Well, what I am certain of is there going to be non-BPS excitation because the potential looks like an exponential wall there. There's a bottom, and then it goes exponentially flat at infinity. And ADS3 times S3 is at the bottom of that, and you can sure as hell oscillate around the bottom. So there are certainly time-dependent solutions where this thing oscillates around the bottom. That must be true.
But eventually the oscillations will die out, right?
Maybe
it's
they keep
S3. It's in a box.
So they'll just
They'll oscillate like that forever.
It's like a steady state.
It'll be some kind of weird ground. It's a graviton gas in a box. And so it's going to be it won't die out until you couple it to flat space.
Yeah.
And then it will leak out in Hawking radiation.
Yeah.
So that's the fuzzball picture of what Hawking radiation ought to be. You should be able to do something really cool, which is a nice solution in ADS3 that doesn't decay. And then the decay comes from coupling it through to flat space. And that I didn't talk about in these lectures. I mentioned it in passing. I said, from the point of view of solving the 6-dimensional BPS equations, you just put 1s into the z's. And it just changes some of the sources. Then it changes the omegas and f's. It does change the Quaffurian conditions. But it's not, from the practical 6-dimensional point of view, it's not much harder to couple it to flat space. It just means you have to solve some more equations, but they're usually not that much harder. Now, but I think the smart way to do it is to really take something that's well known. Take the 10N superstratum. We know exactly how to couple that to flat space, exactly. But you can imagine putting a graviton gas in the ADS3 part that sort of localizes highly at the bottom. And yet the top of it looks just like the 10N superstratum. And we know how to couple that to flat space. So you might be able to make a very simple, effective coupling to flat space where the WKB tunneling of the state that sits at the bottom of the cap, that's thermal graviton gas, thermal graviton gas, then bleeds out through tunneling to flat space. And you'd get an estimate of the Hawking radiation. There might be some really simple, crude estimates you can get from that. And it would all be to do with what's the energy of this excitation, this thermal gas, how deep is the throat, what's the redshift, and then how big is the tunneling barrier to couple to flat space, and you'll get a tunneling amplitude, and you'll get a decay rate, and you'll get the Hawking radiation, and you'll get the, you might even get a thermal distribution if you're really lucky. So putting the graviton gas at the bottom of the ADS3 would be a huge step forward, and then there'll be a lot of. You'd have to work hard to couple it to flat space, but all the techniques are now in place to do that kind of thing. And so, I would say it's not quite a trail of breadcrumbs to the answer. It's a trail of big chunks of cheese, and you can actually sustain yourself on the route, but it's a long route. But the most important first step is something in the bottom of a superstratum that's not BPS, and then you can see how it decays. Anyway. Any other questions or comments?
I guess I have it's a left field question. It may be silly, but is there any way to, or has anybody thought about asymptotically de Sitter with microstates? That could be I don't know if that's a silly question.
It's not silly, but we tried.
Not silly at all.
Okay.
Definitely, yes.
The problem is, easiest would be, so if it's de Sitter, there's no supersymmetry, so you are screwed. Essentially, you need cohomogeneity. It's a function of two variables, no supersymmetry. That's difficult. But we tried actually, first of all, asymptotically anti-de Sitter. Asymptotically anti-de Sitter, there exist these gauge supergravity theories, which have ADS space as a solution.
Wait. You don't mean asymptotically you mean asymptotically ADS5 or ADS4. We already have asymptotically ADS3.
It's ADS3 times S3, and it's actually not, you don't have a black hole in ADS3, you have a black string in ADS3. So
no, but I'm being stupid. We've already got things that are asymptotically ADS3. So what is the value added in saying asymptotically ADS?
Because all the solutions we have are obtained in ungauged supergravity, which comes from compactifying string theory on basically T4 or T something. While if you can get, for example, ADS5 gauge supergravity, if you can get a black hole there, we know that black hole exists. It's the Gutovsky-Real black hole. And for the Gutovsky-Real black hole, which is obtained in gauge supergravity, it's a supersymmetric black hole. It has a lot of supersymmetries, and one can actually build a solution. It's quite painful, but one can do it. And we know the killing spinors. We know gauge supergravity, Nick eats it with breakfast, before breakfast, 5 gauge problems. So I've been trying for 15 years to find if one can get any microstate geometries in this gauge supergravity, and we couldn't. It's a very complicated problem because even if the system of equations is supersymmetric, you don't have linearity. These linear systems we have for superstrata, it only exists in ungauged supergravity and in the 6-dimensional supergravity we are using. If you do gauge supergravity, the system is not linear. So then you don't have the simple thing where you choose a base and then you choose a work factor and so on. And because the system depends on two variables, we could never find a solution. And we tried, and many other people tried, Nick's student, I remember, like, 15 years ago when I came to France, Chetan
Yes.
Gautier, who was like, Nick's student, I mean, he was a postdoc, and, he tried for like, about 1 year to find these things. And, he tried in Saclay, and Nikolai Bobev tried, and everybody and their brother tried. I mean, everybody gave, everybody tried to take a crunch of this, but, essentially everybody failed. It's either that, I mean, the equations are known, everything is known, but it's just setting them up and, finding the supersymmetric solutions and so on. Moreover, there's a theorem by Harvey, Real, and people that the black ring, you cannot build a black ring in this gauge supergravity. You have the Gutovsky-Real black hole, but you cannot build a black ring. Now, historically, there have been many Harvey-Real theorems, which Nick and I showed to be
that's a bit like, this is being recorded. It's a bit unfair, but okay.
It's a bit unfair, but, as we say, as the US saying says, this and $1 is going to get you a coffee. So, right. Theorems are only as valid as, are only as powerful as the assumptions they contain. So now, on the other hand, it may be that the theorem is right and you cannot build black rings. If you cannot build supersymmetric black rings in those geometry, in ADS5, again, asymptotical ADS5 and, gauge supergravity, if you cannot build supersymmetric black rings there, most likely you cannot build microstates either. This is the intuition I have. Maybe Nick doesn't agree with that, but
I think that intuition I completely agree with, except let me pass on a piece of wisdom. When I was an undergraduate, there was an acerbic Russian theoretical physicist about 2 years ahead of me, and he was passing on advice, and he said, "Go not to mathematicians, for they will tell you that you can't do what you bloody well know you can." And so the point being is, you have to go to, when a mathematician makes a statement, you have to go and look very carefully at the assumptions, because that's how you blow the theorem out of the water. You violate one of the assumptions. And so I completely agree with Josef's characterization. If you simply try and look at something with a U1 cubed or U1 to the n gauge symmetry, and you want to make a BPS black hole or microstate geometry, you're not going to succeed, because the fact is, you need it to make a black. If you can't make a black ring, you can't. That means you really can't make a two-centered solution. If you can't make a two-centered solution, you're not going to make a microstate geometry. But I think there's a hole in that. There's a gap in that theorem, and I'm beginning to think that there is a way through which actually. I've been asking myself, having done all this stuff with the holomorphic formulation of the ADS 3 times S3, is there an ADS 5 times S5 analog of this story? And in particular, can you make something that looks like an ADS 5 superstratum? So you start with ADS 5, and then it stabilizes some geometry, and then maybe caps off again in ADS 5 with something in between. And that something in between is going to be possibly stabilizing an S3. It might be also just stabilizing an S1, which would be less boring, but and then what would happen is you'd have something that looks like an ADS3 throat, sorry, S3 throat. Now, that does not fit with Gutovsky-Real, because Gutovsky-Real, remember, what you stabilize to is the horizon of this object. And so with Gutovsky-Real, the horizon geometry is completely weird. It's one of these nil manifolds, as I remember. It's some torus modeled out by something or other. So when you zoom into the Gutovsky-Real black hole, one of the confusions is its horizon isn't, I think it looks like it's a non-compact space, but it's actually compact because it's modeled out by some discrete group, but it looks like it's just a flat, but it is a flat, it's flat. It's not positively curved. So what would be really nice is if you could make some big, fat, round thing that stabilizes, that looks like the horizon. And one thoughts about doing that is that you actually stick an instanton in the middle of it. You stick something which has a non-trivial SU2 charge on it. That would then give you some positive curvature, which might. So the way to drive a hole in the theorems is you add a charge to this object that you haven't thought to add before. And one of the ways you could do it is, because you've got an S3, you can stick an instanton charge in the middle of it, and maybe that's enough to turn the horizon into something reasonable. I have no idea whether that's true or not, but one of the sort of side questions I have that comes out of all this stuff about superstrata is, what's the ADS 5 times S5 analog of everything we've just done? And I suspect there's something there. It's just, you've got to figure out what it is. And the first step is to figure out what's the horizon whose scale you're going to stabilize. When you get, remember, if you take the A goes to 0 limit of a superstratum, it's the BTZ black hole. You know damn well what the horizon is. It's ADS2 times the S1. What's the ADS5 analog of that? Well, you've got to answer the question, what are you going to stabilize? What's the big, and if you want to make a black hole, you better stabilize an S3, because that's this horizon of an S3. So find a way to stabilize the horizon of an S3. Instanton will scream at you because you're looking at, you've got an SU2 gauge group. We have an SU2 gauge group in the superstratum. You've got maps of the 3-sphere into the gauge group. Maybe you can do it with an instanton, and that is not excluded by any of the theorems that are out there. All the theorems that are out there involve U1 gauge groups and gravity and black holes, and you get this really strange black hole that nobody fully understands. In fact, it was a real outlier for a long period. How do you count the entropy of the Grotowski-Rao black hole? And people couldn't do it. They couldn't find out the holographic states of CFT. And then finally, victory was declared in a similar way that the islands declared victory. There was this paper, Murphy, I'm trying to remember who else it was, where they said, oh, we can find this Euclidean saddle point, which counts the states of the Grotowski-Rao black hole. And it was amazing. They could find it, but didn't tell us anything about the microstate structure.
Yeah.
So Grotowski-Rao and ADS5 is a huge open problem, and many people have broken their heads on it. And occasionally there's been little bits of progress, but it's...
This would be some type of S3 embedded in S3 within the S5 or something, I guess.
Well, no, what you should think, okay, go back to the superstratum for a minute. What you should think of the superstratum as being is the following. In terms of the geometry, what are you doing? You start with an ADS3.
Mm-hmm. I'm going to charge my computer.
Yeah.
keep talking. I got to charge my computer.
It's come to that. I've been talking so long now that I've discharged your computer. Okay, so we should shut up in a minute. But let me explain. Superstrata, you start with an ADS3. And then you put a momentum wave on. What does that really mean? It means you add a charge which is localized on a circle, or it's associated with motion around a particular circle. And then, miracle of miracles, what happens is it keeps that circle fat. It doesn't want to collapse or pinch off like it does in ADS3. It keeps it fat, and then you can keep it fat for a very, very long distance in the geometry, and then finally it caps off. So really you should think of the superstratum as saying, I start with an ADS3, and I'm going to stabilize one piece of geometry and keep it large because of some source that I'm going to put around that S1. So now you try and approach the ADS5 geometry in the same way. You say, okay, I've got an ADS5 and I don't want to pinch it off, but what could I stabilize? Well, one thing I could do is I can imagine saying, okay, around the origin in space, it's a 4-dimensional space. Around the origin, there's an S3. Suppose I could keep that fat. So my ADS5, you should think of it as time, a radial coordinate, and an S3. So now, in ADS3, the S3 pinches off to make the bowl of ADS5. But now I'm going to stop the S3 from pinching off. I'm going to keep it fat for a long period and then have it pinch off. That looks exactly like what should be a BMPV black hole. A BMPV black hole is a point source in R41. And that point source in R41 makes a black hole with a horizon that's an S3. So the goal is to stabilize an S3. Mm. Now, it may be utterly impossible to do that, but if you can't do that, you can't make microstate geometries that are 5-dimensional analogs of the superstrata. But Joseph is right, stabilizing an S3, we have completely failed to do that. And in fact, the only supersymmetric black hole we know doesn't have an S3 horizon. It has this really strange nil manifold horizon that we don't understand. So if you read Grotowski-Rao, it's a tour de force, it's an amazing piece of work. But you get to the bottom of this black hole, and it's like, what the hell is that? The horizon is flat. It's just identified. So I think what's missing is there's got to be some fundamental charge that in the ADS, if you want to make it supersymmetric, you've got to add something new to round out the horizon, and then you've got a shot at the microstate geometry. And if I had to guess, I'd say it was an instanton, because what's an instanton? You have to go to SU, you have to go to a gauge supergravity where you have an SU2 gauge group. And then what you can imagine doing is you say, I take the S3 and at infinity, just like you do with instantons, you say, okay, I've got a pure gauge configuration. My boundary condition is pure gauge, but it's the maps of the S3 at infinity into the S3 of the gauge group. That's the instanton number, the winding number of that map.
Oh, yeah,
and then I can look at the configuration that has those boundary conditions. So maybe I can put something that's asymptotically like an instanton. It becomes pure gauge, but with winding number n. And maybe that's going to have enough energy density to overcome whatever shit's going on in the ADS5 that screws up the horizon and makes you a big fat thing at the bottom. Anyway, that's the only reason why well, there are several reasons why I'm doing it. It's a cool way of putting topology into a black hole. The other reason I'm saying that is that the no-go theorems that Harvey's proved are, you know, I believe they're right, but like all mathematical statements, you have to look at what they've forgotten to put in. Give me 1 second. You're having to dog it way down because I might not join you in about 10 minutes. Okay. Okay, so anyway, I don't know whether any of this will work. It's one of those problems that the warning that Joseph gave is a good one. You know, a lot of smart people have broken their heads on trying to get black holes, supersymmetric black holes in ADS5. It's really hard. And, you know, Chetan worked really hard on it. He got, you know, you can push the equations to a nicer and nicer and nicer form, but the bottom, if you remember when I was talking about the layers of equations, there's layer 0, which is the geometry, and then there's layer 1, and there's layer 2, and in fact, you can break it into 3 layers if you're in 5 dimensions. But what happens when you add the cosmological constant is that the cosmological constant couples layer 1 to layer 3. So it's no longer this upper triangular structure. It says, you've got to know the answer to the bottom layer, feed it back into the top layer again, and that coupling is the cosmological constant. So it's an intrinsically horribly nonlinear system. So that layer decomposition doesn't work, and the thing that breaks it is the cosmological constant. There's a sort of another way of thinking about microstate geometries in ADS, which I think is the right way to think about it, which maybe might be more up to Bogdan's direction. Look, if I go to a cosmological ADS or DS, it doesn't matter. If the cosmological constant is small compared to the scale I'm large compared in length scales, it's large compared to where I'm living. You know, we don't know in our solar system there's a cosmological constant. It's just the way that the length is too long. The horizon length is much larger than the solar system. So when I put planets and stuff, it's like I'm in flat space. So when you bubble geometries and you make superstrata, you make all these things, they're supersymmetric in my solar system because I'm making them, you know, on scales of kilometers or maybe scales of light minutes. I'm not making it on scales of 13.7 billion light years. So if I work locally, I don't know there's a cosmological constant. So I should be able to do every single bubbling, sort of magical, wonderful thing that I've done in ADS or DCS. It doesn't matter. I should be able to do that. But what probably happens is the supersymmetry I'm trying to preserve for my BPS microstate geometries is incompatible with the supersymmetries that ADS will have. And so the argument would be that the cosmological constant, there must be bubbling geometries, there must be all of these things, but the cosmological constant will come in and break the supersymmetry, but only on very, 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 very weakly, but very, very small cosmological constants. So what I'm saying is everything I'm talking about must be able to be doable in ADS5, ADS whatever, or it must be doable in DS, but it will all be non-supersymmetric because the supersymmetry breaking will be at the scale of whatever the small constant. The small supersymmetry breaking parameter is the scale of my bubble compared to the scale of the cosmological constant. And that can be made arbitrarily small.
Right, because, yeah.
So I believe that bubbling geometries are part of de Sitter universes, they're part of anti-de Sitter universes. You should be able to do everything I've said, but the cost will be that the supersymmetry of ADS and the supersymmetry of microstate geometries perhaps is incompatible. And therefore, one doesn't like the other. Wow, we've still got a few people left. So that's the last lecture, guys. I think my brain is fried. Any other last questions? Or we'll...
Thank you.
Thanks a lot.
Thanks a lot.
Thanks.
Thank you, Nick.
You're welcome, and I hope it was useful. So anyway, we'll talk. I'm sure we'll.